We are looking at the foundational instructions, the cellular choreography, for the most complex structure in the entire human body, the head and neck.
And if we connect this to the bigger picture, the reason this region demands such a, complex discussion is that the head and neck are fundamentally distinct from the rest of the body, the trunk, the limbs.
Right. It's not just more of the same.
Not at all. The sources highlight that craniofacial development utilizes unique signaling pathways, specialized mechanisms. And it demands an extraordinary degree of conserved, organized precision that you find across all vertebrates.
It's the ultimate convergence zone, isn't it?
That's the perfect way to put it. It's where every major sensory organ, all these intricate skeletal structures and major vascular networks must all assemble and link up in a relatively small space all at once.
And when you look at the adult human, the sheer density is just astonishing. Think about it. Eyes, ears, nose, tongue, brain protection, the chewing apparatus, airway management, the beginnings of the digestive tract. It's all crammed right here.
Right.
The margin for error must be microscopically small.
It is. The area we're tracing, developmentally speaking, is everything cranial to the occipital cervical junction, that invisible boundary line where the skull meets the spine.
So south of that line, things are more standard.
You could say that. Caudal to that line, development follows a more traditional segmented plan. It relies on paraxial mesoderm segmenting into somites that build the trunk muscles and the vertebral column. Cranially, that whole plan is, it's tossed out, and we rely heavily on these specialized, highly mobile cell populations.
And our mission today is to trace that journey, how the skull, the face, the neck muscles, the nerves, the carotid arteries all form from these initial, almost impossibly simple bulges and pockets, what we call the arches and the pouches. And crucially, we want to deliver those genuine aha moments about your own anatomy.
For example, understanding this process explains why seemingly disparate structures, like your massive lower jawbone, your tiny cheekbones, and the microscopic ear ossicles, are all linked through the same single dedicated nerve, the trigeminal.
It all comes back to their shared origin.
It's all about their shared embryonic origin. That's the wiring puzzle we really need to solve today.
Let's start with the master builders themselves. So if we're building a complex structure like the head, we need specialized architects. And here's where it gets really interesting. The foundation of the head, specifically, most of the skeletal and connective tissue, doesn't come from the typical mesoderm, which builds the body's skeleton and heart, but from these remarkable migratory cells, the neural crest cells, or NCCs.
Exactly. And this distinction is vital because it explains the unique flexibility and, the developmental freedom of the head. When we talk about the craniofacial skeleton, the loosely organized connective tissue that forms it is primarily referred to as secondary mesenchyme.
Secondary mesenchyme.
It's secondary because it's derived from the neural crest or the ectoderm, rather than the primary mesenchyme, which comes from the mesoderm that builds the rest of the body.
Wait, I need a clearer picture of that distinction. When we talk about mesenchyme, what are we picturing? Is it like a solid tissue or something else entirely?
Think of mesenchyme as a kind of biological jello. It's a loosely organized embryonic connective tissue defined by the fact that the cells are suspended in this rich, watery extracellular matrix, the ECM.
So they're not locked in place?
Not at all. The cells aren't tightly bound in sheets like epithelial cells are. This ECM, which is rich in things like fibronectin and hyaluronic acid, acts as a superhighway for these NCCs. It allows them to crawl through the embryonic landscape to get to their destination.
So primary mesenchyme builds the body.
Primary mesenchyme from the mesoderm forms structures like the heart and deep body fascia. But this secondary mesenchyme from the neural crest carries the specific positional identity needed to become, say, a jawbone or a nose cartilage.
That distinction makes sense. Specialized jobs need specialized material. But before the NCCs can migrate and build, they have to transform from stationary parts of the neural tube into these mobile architects. That foundational cellular shift, the epithelial to mesenchymal transition, the EMT, that's a huge deal, isn't it?
Oh, it's one of the most critical transitions in all of development, and it's one that gets repurposed later in life for processes like wound healing and, unfortunately, metastasis in cancer.
Wow.
So NCCs originate as these stationary, tightly bound epithelial cells right at the lateral edges or the crest of the neural plate and then the neural tube. The EMT is the mechanism where these stationary sort of brick-like cells have to intentionally lose their tight cell-to-cell adhesions.
You're break free.
They essentially dissolve their connections, detach from the neural tube, and transform into mobile, migratory mesenchymal cells.
It's like switching a brick from being part of a stable wall to becoming an independent, moving architect with its own GPS. But what allows them to achieve that extreme plasticity and, that variety?
Their developmental portfolio is truly staggering. I mean, cranial NCCs differentiate into an astonishing variety of tissues, far beyond what traditional mesoderm can achieve.
Like what? What are we talking about here?
We're talking about almost everything non-neural or non-muscle in the face. The entire skeletal and connective tissue framework of the face and neck, so cartilage, bone, ligaments, the dermis of the face.
Okay.
Components of the cranial sensory ganglia for nerves V, 7, nice, and X, specific glands, parts of various nerves, and even pigment cells, the melanocytes.
That is an immense range. If one cell type can form bone, cartilage, and nerve tissue, how does the embryo manage this incredible potential? I mean, how do they know what to become once they arrive?
That control is deeply rooted in genetic segmentation. And this is where we need to spend some time, because this is where the Hox gene story comes in.
Ah, the body plan genes.
Exactly. The cranial NCCs are unique because they largely suppress the expression of Hox genes, which are the master regulatory genes that define positional identity along the body axis in the trunk. Think of Hox genes as a restrictive set of rules.
So the trunk NCCs, which become the dorsal root ganglia and autonomic nerves, they're highly restricted by their Hox code.
They are. But cranial NCCs, lacking most of those Hox gene constraints, have what researchers call developmental freedom. They are essentially blank slates. But, and this is the key, they gain their identity, their specific instructions to become a jawbone versus a throat cartilage from the local environment they migrate from.
So the key isn't their destination, it's their source, the segmented hindbrain.
Precisely. The organization relies entirely on the segmentation of the developing hindbrain into these segments called rhombomeres numbered R1, R2, R3, and so on. These rhombomeres act as migration gates, and they are the core of the organizational planning.
Can you elaborate on the physical mechanism? Are these rhombomeres just static borders, or are they dynamic barriers?
They're dynamic transient segments. Cells within a specific rhombomere express adhesion molecules and signaling factors that keep them clumped together, which effectively establishes boundaries. But what's crucial is that neural crest cells only emerge and migrate from even-numbered rhombomeres R2, R4, and R6, R7, and curiously, also from R1.
Wait, only the even-numbered ones? What happens to the odd ones?
The odd-numbered rhombomeres R3 and R5 have self-signaling mechanisms that actually prevent their NCCs from migrating. They effectively act as barriers or dead ends.
Wow. So the embryo has specific migration gates and no-fly zones built right into the nervous system.
It's a remarkable level of control. And these streams of cells dictate the future identity of the structures. So NC cells originating from R1 and R2 specifically migrate to form the structures of the first pharyngeal arch.
Okay.
Cells from R4 feed the second arch, and cells from R6 and R7 feed the third arch and the more caudal structures.
That makes the early embryo look far less like a random collection of cells and more like a carefully mapped, pre-programmed delivery system. If there's a genetic error in, say, R4, you know exactly which skeletal structures are going to be affected downstream.
That is the power of the segmentation code. The identity of the future face and neck is coded into the point of origin in the hindbrain. For instance, if you transplant NCCs destined to form Arch 2 from R4 into the region normally destined for Arch 1 from R2.
What happens?
Those R4 cells often still try to form Arch 2 structures, like the stapes bone from the ear, but in the wrong location. This proves they carry a strong, intrinsic, genetically determined identity based on their rhombomere origin.
Speaking of complex interactions, while the NCCs handle the vast majority of the connective tissue and skeleton, they can't build the sensory systems alone. That brings us to the second foundational component, the ectodermal placodes.
You know, what's fascinating here is that the creation of the complex sensory apparatus, the eyes, the internal ear, the ganglia, requires these specialized thickenings of the surface ectoderm, the placodes.
So these are totally different cells.
Entirely distinct cell populations from the neural tube and the migrating crest cells. But they have to work alongside them, in perfect concert.
This collaboration is essential for the nervous system, right? What structures emerge from these thickened ectodermal regions?
Placodes give rise to structures fundamental to sight, smell, and hearing. We're talking about the crystalline lens of the eye, the lining of the nasal cavities, the complex sensory structures of the internal ear, and critically significant portions of the peripheral sensory ganglia.
The sensory ganglia.
Yes, the specialized sensory afferents for the trigeminal V, facial 7th, glossopharyngeal 9s, and vagus X nerves.
So that's the key insight. The sensory ganglia, the nerve centers for touch, taste, and sensation in the head, they are not a single source product.
They are a mosaic. The NCCs provide the structural framework, the connective tissue sheath, and perhaps some glial cells, while the placodes provide the actual sensory neurons for these ganglia. For instance, the sensory components of the large trigeminal ganglia are a mix of cells derived from both the migrating neural crest and the ectodermal placodes.
That's incredible.
This collaborative development really underscores the integration required to build the nervous system of the head, ensuring motor control, which is mostly arch-derived mesoderm, and sensory perception from the placode and NC are perfectly aligned in the final structure.
Okay, we've moved from the cellular blueprints, the NCCs and placodes, to the structural blueprint, the assembly line. So what does this all mean for the face and neck?
Well, the migrating NCCs, following the directions set by their rhombomere origin, they aggregate and form these segmental bulges on the side of the embryonic pharynx. These are the pharyngeal arches.
And they are truly a masterpiece of developmental segmentation.
They really are. These arches are often referred to as the ancient evolutionary blueprint. They're the fundamental repeating units, homologous to the structures that become the gill arches in fish, that define the structural basis of the head and neck in the human embryo.
And they pop up pretty early.
They appear sequentially, starting around week 4 of gestation.
How many do we start with, and what is the standard layout of one of these structural modules?
We typically observe 5 or 6 arches, numbered 1, 2, 3, 4, and 6. It's really important to note that arch 5 is usually rudimentary or vestigial in humans.
So it's there, but it doesn't do anything.
It appears transiently, and then it just disappears, leaving no lasting adult structures behind. The remaining arches form a really elegant modular system.
Describe that module. How is it constructed?
Each arch is a self-contained unit. It's covered externally by a layer of ectoderm, which sinks inward to form the pharyngeal clefts or grooves.
Okay, so that's the outside.
And is lined internally by endoderm, which bulges outward to form the pharyngeal pouches.
And what's packed inside that core? What's in the middle?
The core of each module contains the specialized mesenchyme derived from the neural crest for the skeletal elements and from paraxial mesoderm for most of the muscles. And critically, each arch contains a dedicated cranial nerve.
A dedicated nerve.
That supplies both motor and sensory function to that entire module. It also has a specific artery, which is one of the aortic arch arteries, and the foundational skeletal element, which always starts as cartilage.
So it's an entire segment of the body, complete with its own nerves, blood supply, muscles, and bones, all packaged together before development even really begins.
Exactly.
This is why tracing their derivatives is so neat. Everything that comes from arch 1, for example, shares the same nerve.
Precisely. Let's trace that evolutionary legacy by detailing the derivatives of these arches, because it's really where you see the logic.
Let's do it. Starting with arch 1, the mandibular arch. This arch forms the entire lower third of the face.
The mandibular arch has 2 components: the mandibular prominence, which forms the lower jaw and lip, and the maxillary prominence, which forms the upper jaw, cheek, and part of the palate. And its skeletal element starts as Meckel's cartilage.
Meckel's cartilage is famous because it mostly disappears, correct?
It largely regresses, yes. It acts primarily as a developmental scaffold, directing the formation of the lower jaw, the mandible, which ossifies via intramembranous ossification around the cartilage scaffold.
But not all of it disappears.
Its fate is dual. The cartilage itself doesn't become the mandible, but the dorsal ends of Meckel's cartilage do not disappear. They ossify directly to form 2 of the 3 middle ear ossicles, the malleus, which is the hammer, and the incossus, the anvil.
Wait, hold on. The bones we use to chew, the mandible, are formed around the cartilage scaffold, but the tiny bones we use to hear are formed from that same cartilage scaffold. That's a phenomenal connection.
It is a deep, deep connection.
Yeah.
And the ligamentous remnants of Meckel's cartilage also form the anterior ligament of the malleus and the sphenomandibular ligament, further linking the ear and the jaw.
What about the muscles and nerves that are paired with this complex skeletal structure?
The muscles are the powerful muscles of mastication. The temporalis, the masseter, and the medial and lateral pterygoids. It also forms accessory muscles like the mylohyoid, the anterior belly of the digastric, the tensor tympani.
The tensor tympani, that's in the ear, right?
That's the one. It tenses the eardrum. And also the tensor veli palatini, which helps tense the soft palate. The nerve that controls all of these muscles and provides sensation to the entire lower face is the mandibular division of the trigeminal nerve, V3.
Which is why when you feel a toothache or chew food, The signals are traveling along the same foundational pathway.
Exactly. It's one neat package that explains the entire functional unit of the jaw.
And what about its artery?
The first aortic arch artery is highly transient. It's present very early, but it largely regresses, contributing only slightly to the maxillary artery, which supplies the deep structures of the face.
Okay, moving on to arch 2, the hyoid arch. This arch governs the structure of the neck and, perhaps most notably, facial expression.
Its cartilage, known as Reichert's cartilage, is dedicated to more delicate structures. It forms the last ear ossicle, the stapes, the stirrup, completing that chain of sound transmission.
Ah, so all 3 ear bones are from arches 1 and 2.
That's right. It also forms the styloid process of the temporal bone, the stylohyoid ligament, and, importantly, the lesser horn and the upper part of the body of the hyoid bone, which anchors the tongue and larynx.
And the muscle group here includes some of the most visible muscles we have, plus one of the smallest.
Indeed.
Okay.
It forms the entire sheet of the muscles of facial expression. The orbicularis oculi, the buccinator in the cheek, the platysma in the neck, the posterior belly of the digastric, and the stylohyoid. And the tiny muscle it forms is the stapedius muscle, which attaches to the stapes.
And the nerve.
The nerve for arch 2 is the facial nerve.
Okay, here's the big aha moment for arch 2. The nerve that allows us to smile, frown, and make all expressions, nerve 7, is intrinsically linked to the tiny muscle that protects our inner ear from loud sounds, the stapedius. Because they were both packaged together in that second pharyngeal arch module before the structures migrated to their final distant locations.
It is a perfect demonstration of the developmental legacy. The stapedius muscle contracts reflexively to dampen loud noises, protecting the delicate internal ear structures. Its innervation by the facial nerve is it's a historical accident of embryogenesis.
It links the most complex, socially significant function facial expression with one of the most fundamental protective reflexes.
You've got it. And like arch 1, the second arch artery is primarily transient, contributing to the small stapedial artery, which often disappears later in development.
Okay, next up, arch 3, the mid-neck stabilizer. This seems to have a simpler but perhaps more focused output.
Arch 3 is less sprawling in its skeletal and muscular derivatives for sure. Its cartilage forms the greater horn and the lower part of the body of the hyoid bone, providing a critical anchor point in the middle of the neck.
And just one muscle.
The sole muscle derivative is the stylopharyngeus, which helps elevate the pharynx during swallowing. And the dedicated nerve is the glossopharyngeal nerve, IX, which is crucial for taste and sensation from the posterior tongue and for pharyngeal motor control.
But its arterial contribution is vital for the brain.
Extremely vital. The arch 3 artery forms the proximal part of the common carotid artery on both sides, and the distal part of arch 3 combines with the dorsal aorta to form the crucial internal carotid artery. This whole system is dedicated to supplying blood to the developing brain.
Finally, we combine arches 4 and 6 because they cooperate closely in building the framework of the larynx, the voice box. Why are they typically discussed together?
They collaborate sequentially to build the lower throat. The mesenchium from arch 4 forms the prominent thyroid cartilage and the cricothyroid muscle. Arch 6 forms the cricoid cartilage and the intrinsic laryngeal cartilages, like the arytenoids.
And the muscles.
The muscles derived from these caudal arches are the pharyngeal constrictors, most of the palatal muscles, and the intrinsic muscles that operate the vocal cords.
And the nerves here are branches of the vagus, a very complex nerve, nerve X.
Yes, the vagus nerve X splits its contribution based on the arch origin. The superior laryngeal branch innervates the arch 4 derivatives, and the recurrent laryngeal branch innervates the arch 6 derivatives, specifically the intrinsic laryngeal muscles necessary for voice production.
This brings us to a crucial developmental artifact that makes perfect sense once you know the history. The bizarrely circuitous route of the recurrent laryngeal nerve. It travels all the way down into the chest and loops back up. Why on earth does it do that?
This is one of the most famous examples of anatomy being dictated by an early embryonic event. The nerve's extensive looping route is a direct reflection of its caudal origin in arch 6. It has to follow the path of the 6th aortic arch artery.
Which is way down in the chest.
Exactly. It loops into the thoracic region to connect to the developing pulmonary system. Even as the embryo grows and the arch structures reorganize and descend into the neck, the recurrent laryngeal nerve, which supplies the arch 6 musculature, remains hooked around that descending arch artery remnant.
So if the embryo had a different aortic arch system, we might have a much shorter, more direct route for that nerve.
Absolutely. Its path is anatomically inefficient in the adult, but developmentally it's a necessary consequence of following the descending aortic arch system. This principle, that nerves follow their associated arteries and arches, even when those arches regress or migrate, is key to understanding the deep connections established during embryogenesis.
Okay, we've covered the external framework, the arches, but that internal endodermal lining forms critical pockets, the pharyngeal pouches, that create vital internal organs, mainly glands and passages.
Right. If the arches are the external scaffolding, the pouches are the internal linings that transform into glandular tissue. The endodermal lining of the pharynx forms 4 pairs of internal pouches.
Let's look inside. What comes from pouch 1?
Pouch 1, located between the first and second arch segments, is focused on auditory structures. It expands laterally to form the lining of the tympanic cavity, which is the middle ear space, and the auditory tube, or eustachian tube.
The one that connects the middle ear to the pharynx for pressure equalization.
That's the one.
So arch 1 gives us the malleus and an incus. Arch 2 gives us the stapes, and pouch 1 gives us the dedicated air-filled space where they sit, plus the plumbing to keep the pressure correct. It's a highly integrated system.
It is entirely integrated. Pouch 2 remains relatively simple structurally. It forms the primordial tissue that becomes the palatine tonsil, the lymphoid tissue situated near the pharynx.
Then we get into the major migrators, pouches 3 and 4, which are famous for swapping positions.
Yes, this is a classic puzzle of anatomical location. Pouch 3 is highly influential. It forms 2 critical endocrine structures, the inferior parathyroid glands and the thymus.
And the pouch 3 derivatives are destined to migrate the farthest. Why do they migrate so far?
The thymus, which plays a massive role in early immune system development, must descend significantly into the thorax, right down into the chest cavity. As the thymus pulls away, it drags the pouch 3 parathyroid tissue with it. Consequently, this tissue ends up in the inferior position in the neck.
And pouch 4?
Pouch 4 forms the superior parathyroid glands and the ultimobranchial body. Since the pouch 4 derivatives don't migrate as extensively as the pouch 3 and thymus complex, they end up in a slightly more cranial position. They're located superiorly to the pouch 3 derived glands.
It's a migration reversal.
A classic counterintuitive fact of head development. The ultimobranchial body is also fascinating because it integrates into the thyroid gland to contribute the parafollicular C cells, which produce the hormone calcitonin.
We can't forget the exterior structures, the pharyngeal clefts or grooves. What is their fate?
The external grooves, or clefts, between the arches are lined by ectoderm. The second, third, and fourth clefts usually disappear entirely. The second arch grows caudally downward and overgrows the clefts, covering them completely and eventually merging with the cardiac prominence.
What does that process create?
The resulting structure is the smooth contour of the adult neck. However, the first cleft is unique. It persists and sinks inward to form the external acoustic meatus or external ear canal.
And if those caudal clefts fail to disappear, that results in a common clinical anomaly.
Absolutely. Failure of the second, third, or fourth clefts to regress completely, or if the remnants of the pharyngeal structure persist, leads to the formation of branchial cysts or sinuses.
Where do you see those?
They're typically seen laterally in the neck region, often presenting as a palpable swelling in infants or young adults. It provides a direct clinical correlation to the failure of this necessary developmental regression. It's a physical bookmark, marking where the embryonic gill structure used to be.
We've built the segmental structures and the specialized organs. Now we need the circulation system. The complexity of the arteries in the head and neck is, I think, profoundly underappreciated, as the entire system undergoes a complete replumbing.
It really does. The embryonic heart first pumps blood into the simple bilateral system of 6 aortic arteries, I through 6, that shunt blood from the primitive heart through the pharyngeal arches and into the dorsal aorta.
And this entire system gets remodeled.
It undergoes one of the most dramatic remodeling efforts in the body. Vessels regress completely, vessels fuse, others expand extensively, all to form the asymmetric adult pattern.
Let's trace the sequential fate of these 6 pairs of arches, starting with the early regulators. What happens to the first 2?
Arches the first and 2 are the earliest to form and the earliest to regress. They are highly transient, providing temporary supply to the mandibular and hyoid regions when those arches are dominant. The remnants left behind are quite small.
So not much left of them.
Not much. Arch 2 contributes to the maxillary artery, and arch 2 contributes to the small stapedial artery, which, as we said, often regresses or disappears later in human development.
Arch 3 seems to be the first one with a permanent major role in adult circulation.
Critically permanent. Arch 3 is the architect of the carotid system. It forms the proximal part of the common carotid artery on both sides. Distally, arch 3 combines with the dorsal aorta to form the crucial internal carotid artery.
And the internal carotids are essential.
Absolutely essential because they ensure the developing brain has an adequate and protected blood supply.
And arch 3 is where the massive asymmetry of the great vessels begins, leading to a completely different fate on the left versus the right side.
That is the pivotal divergence point that sets the adult human circulatory pattern. Arch 3 contributes to the major arch of the chest, but it does so differently on each side.
Okay, describe the left side.
On the left side, arch 3 expands enormously. It forms the segment of the arch of the aorta that lies between the origin of the left common carotid artery and the left subclavian artery. It becomes the magnificent sweeping arch we recognize in adult anatomy.
And the right side is totally different.
Totally different. On the right side, arch 3 contributes to the proximal segment of the right subclavian artery. This explains why the vessels coming off the aorta are asymmetric. The left common carotid and left subclavian arise directly from the aortic arch, which is from arch 3.
Right.
While the right carotid and right subclavian must first branch off the brachiocephalic trunk.
What about arch V? You mentioned that one earlier.
Arch V is truly a placeholder. It is typically rudimentary. It often forms briefly and then just disappears, reinforcing the idea that this is an ancient template that vertebrates inherited, even if all the segments aren't used in humans.
And finally, arch 6, the pulmonary arch. This one is inextricably linked to the developing lungs and fetal life.
Yes. Arch 6 forms the proximal parts of the pulmonary arteries on both sides.
Yeah.
This is its permanent destiny, supplying the lungs. Now, the distal connections are radically different between the right and left sides, based on the requirements of fetal circulation.
Walk us through that distal connection difference.
Okay, so on the right side, the distal portion of arch 6 regresses entirely. It's just not needed anymore. However, on the left side, arch 6 maintains a vital connection to the dorsal aorta. This connection is the ductus arteriosus.
That shunt is absolutely essential during fetal life. Why is this bypass so necessary before birth?
Because the fetal lungs are non-functional. They're collapsed and filled with fluid, which means their resistance to blood flow is extremely high. The fetus cannot waste energy pumping high volumes of blood through resistant vessels.
So the ductus arteriosus is a bypass.
It acts as a high-volume vascular bypass. It shunts about 90% of the blood flowing through the pulmonary artery away from the non-functional lungs and directs it immediately into the dorsal aorta for systemic circulation. This allows the fetus to oxygenate its tissues via the placenta without relying on the lungs at all.
So the moment the baby takes its first breath, that entire physiological structure is redundant and potentially dangerous.
Exactly. Shortly after birth, dramatic physiological changes occur. Lung function begins, pulmonary vascular resistance drops immediately, and circulating blood oxygen levels increase rapidly. These changes trigger the ductus arteriosus to constrict and close.
And it becomes?
It undergoes fibrosis and remodeling over the first few days or weeks of life to become a non-functional fibrous remnant, the ligamentum arteriosum.
And the failure to close is a significant clinical issue.
Failure of this necessary regression results in a patent ductus arteriosus, or PDA. This defect allows blood to shunt from the high-pressure aorta back into the low-pressure pulmonary artery, leading to volume overload in the lungs. It requires medical intervention to prevent heart failure and chronic lung issues.
So the ductus arteriosus is a perfect example of a structure that is absolutely critical for one life stage, but must be perfectly destroyed for the next.
Precisely.
So the arteries are the complex supply lines. But the head also requires an elaborate drainage system, the veins, which undergoes a radical and often less intuitive rearrangement than the arteries.
The venous system starts with blood draining via the primary head vein system, which is this complex, diffuse network of vessels. Initially, the drainage is handled by vessels like the proatic vein, which drains the forebrain region, and the cardinal veins, which handle the rest of the body drainage.
But the adult pattern is dominated by the robust, centralized internal jugular system. How does that familiar structure emerge from this network of thin-walled vessels?
The transition is complex. It involves the regression and fusion of several parallel vessels. The primary head vein system, which is initially fast, regresses in its anterior region. A new, much more focused route, the internal jugular vein, develops from the remaining caudal segment of the primary head vein.
So it consolidates the flow.
It does. This emerging jugular vein then connects caudally to the anterior and posterior cardinal veins, effectively reorganizing the entire upper body drainage pathway.
So the internal jugular system is essentially the reorganized, prioritized main channel of the earlier head vein network.
Precisely. And this reorganized trunk then serves as the nexus for all the accessory drainage. The veins associated with the face and scalp, like the facial and superficial temporal veins, then later develop connections in anastomosis with this newly established internal jugular system.
It's a phased approach.
Build the main highway, then construct the on-ramps. That finalizes the robust, efficient adult drainage pattern that manages the massive cerebral, facial, and neck blood return.
We now enter the process of facial sculpting, a period of extremely precise fusion that happens remarkably fast. The development of the face, occurring roughly between week 4 and week 10, is one of the most visible and potentially error-prone steps in human embryology.
It truly is a geometric puzzle that defines who we are. The face essentially starts as 5 separate, prominent masses of mesenchyme, the primordia surrounding the somodium, which is the primitive mouth opening.
And these 5 pillars of tissue have to grow and fuse perfectly.
They must grow, migrate, and precisely fuse together to form the adult face. The critical insight here is that the face does not grow uniformly. It grows in pieces that must meet perfectly.
Let's identify these 5 initial masses of tissue.
Okay, the 5 major primordia are the single median front nasal process, which forms the forehead and the bridge of the nose.
Just one of those.
One of those. Then we have 2 pairs of bilateral structures. The paired maxillary processes, which will form the cheeks, the upper jaw, and the lateral parts of the upper lip, and the paired mandibular processes, which form the lower jaw, lower lip, and chin. The mandibular processes are actually the first to fuse in the midline, forming the chin and lower jaw early on.
The first step for the upper face involves the nasal structures, which begin as simple thickenings.
Yes. The nasal placodes, these thickenings of ectoderm on the surface of the front nasal process, they sink deep into the surface, forming the nasal pits. This sinking process causes the surrounding mesenchyme to swell and differentiate into 2 key structures.
And what are those?
The medial nasal processes on the inside, bordering the midline, and the lateral nasal processes on the outside, forming the sides of the nose.
And the upper lip is where the critical fusion occurs, requiring 3 of those processes to meet up.
Correct. The upper lip is formed by the fusion of the 2 medial nasal processes in the midline, which form the philtrum, that groove under your nose, and the central part of the lip. Crucially, these median structures must then fuse laterally with the adjacent maxillary processes on either side.
Which form the rest of the lip.
The rest of the upper lip and the cheeks, yes.
That fusion line is sensitive. Failure to complete this fusion plane correctly has massive clinical consequences.
Failure of the medial nasal processes to merge smoothly and completely with the maxillary processes results in a cleft lip. Because the medial nasal process contributes to the central part of the upper lip and the primary palate, an error here affects both structures. This fusion process is ongoing and involves differential growth, not just a simple merging, which makes the timing absolutely essential.
Okay, so once the external face is fused, we need to create the internal sealing, the palate, which separates the mouth from the nose. This process also happens in 2 distinct phases that must successfully meet and fuse in the middle.
This is a complex mechanical and cellular process. As you noted, the palate has both a primary and a secondary component. The primary palate is formed early by the deep structures derived from the medial nasal processes merging with the maxillary processes.
So that's the front part.
That's the small segment that forms the frontmost part of the hard palate, the area right behind your upper incisors.
And the bulk of the hard and soft palate comes from the secondary phase.
Yes, the secondary palate forms the vast majority of the hard and soft palate, posterior to that primary segment. It is formed by 2 lateral shelves, the palatine shelves, which grow horizontally inward from the inner aspect of the maxillary processes.
But initially they grow vertically downward, hanging on either side of the tongue.
That's the key intermediate step. The tongue occupies a very high position in the nasal cavity early on. Around week 10, a dramatic, rapid mechanical shift occurs. The tongue drops down and moves out of the way.
And that clears the space.
Once the space is clear, the 2 palatine shells rapidly elevate from their vertical hanging position to a horizontal plane rising above the tongue. They then must meet and fuse in the midline, successfully separating the oral and nasal cavities.
And the nasal septum has to meet them.
The nasal septum must also descend fully to meet the fused palate shelves.
That physical movement of the tongue out of the way sounds like a major bottleneck in the process.
It is absolutely crucial. If the tongue fails to descend or the shelves fail to elevate in time, or if the shelf tissue is just insufficient, the fusion process is disrupted.
So the primary failure point here is the failure of those shelves to elevate and fuse.
Exactly. Failure of the lateral maxillary shells to fuse results in a cleft palate, which can range in severity. This defect prevents the establishment of a complete barrier between the mouth and the nasal cavity, causing issues with feeding, speech, and recurrent infections.
If you want a perfect example of developmental complexity and nerve input chaos, look no further than the tongue. It requires components from at least 3 and possibly 4 different arches to build it, leading to a crazy, complex amount of nerve input.
The tongue is a perfect illustration of the segmental origins of the head, all jammed together into one structure. It develops from several distinct swellings on the floor of the pharynx, and its resulting complexity is reflected in its 4 different cranial nerve supplies.
Let's break down the sources for the body of the tongue, the anterior 2/3.
Okay, the anterior 2/3 of the body is derived primarily from the mesenchyme of the first pharyngeal arch, the mandibular arch, specifically from the 2 distal lingual swellings, and the midline tuberculum impar.
So because of that arch 1 origin,
Its general sensory innervation for touch, pain, temperature is provided by the lingual nerve, which is a branch of the mandibular division of the trigeminal nerve, V3.
okay, but what about taste?
Taste sensation is provided by the chorda tympani, which is a branch of the facial nerve, 7th, which kind of piggybacks along with the V3 nerve pathway.
So V3 handles the feeling, and 7th handles the taste for the front of the tongue. That's a collaboration between arch 1 and arch 2 nerves already. What about the posterior 3rd?
The posterior 3rd, the root, comes primarily from the mesenchyme of the 3rd pharyngeal arch, from the copula and hypobranchial eminence. Its dominant innervation for both taste and general sensation is the glossopharyngeal nerve, the dedicated nerve of arch 3.
And there's that 4th arch involvement at the very back.
Yes. The very posterior part of the tongue, around the epiglottis, is derived from the 4th arch and is supplied by the superior laryngeal branch of the vagus nerve, X.
Wait, hold on. That sounds like a wiring nightmare. We have V3, 7, 9, X, and X all handling feeling and taste, all coming from different origins. How does the embryo prevent those sensory signals from crossing or mixing up?
The integrity is maintained because these nerves migrate with their associated arch tissue, but the lines of demarcation remain remarkably clear. However, here is the final crucial twist.
Oh, there's more.
The muscles that move the tongue, the intrinsic and extrinsic muscles, do not come from the pharyngeal arches at all.
Where do they come from, and why is that important?
They are derived from occipital somites, which are segments of paraxial mesodome from the very caudal end of the embryonic head region. These somites migrate cranially, bringing their own dedicated motor nerve with them, the hypoglossal nerve.
So that's why 12th is purely motor.
This is why the hypoglossal nerve is purely motor, supplying all the tongue muscles, while the sensory and taste functions are handled by the other 4 cranial nerves. The tongue is truly a developmental chimera, a magnificent structure built from 4 different segmented sources and then invaded by muscles from the trunk.
Finally, within the jaw structures, we have the specialized complexity of teeth. This isn't just bone. This is a highly regulated epithelial mesenchymal conversation happening deep within the developing jaw processes.
Tooth development, or odontogenesis, is a prime example of continuous reciprocal induction between the oral ectoderm, the lining of the mouth, and the underlying neural crest-derived mesenchyme. It proceeds through sequential named stages, starting around week 6 to 10.
Can you elaborate on that induction? What are the key cellular signals?
Initially, the ectoderm signals the underlying mesenchyme to condense. Then the condensed mesenchyme signals back to the ectoderm, directing it to proliferate and organize. This back-and-forth conversation involving specific growth factors like FGF and BMPs dictates the shape and location of the tooth crown.
What are the sequential stages of this dialogue?
It starts with the placode stage, where the oral ectoderm thickens, forming the dental placode. This thickened tissue then grows like a small bud into the underlying mesenchyme in the bud stage. As growth continues, the epithelium begins to form the enamel organ surrounding the mesenchyme, which is now called the dental papilla in the cap stage.
And that's when the shape is defined.
The future crown shape is beginning to be defined, yes.
Yeah.
And the final critical differentiation happens in the bell stage.
So what happens in the bell stage?
The bell stage is when the 2 cell lineages, the epithelial or ectoderm component and the mesenchymal or neural crest component, differentiate into their specialized mineral-producing roles.
Detail those roles for us.
Okay, the inner layer of the epithelial enamel organ differentiates into ameloblasts. These are cells derived from ectoderm that produce and lay down enamel, which is the hardest tissue in the human body.
And the mesenchyme.
Simultaneously, the cells of the dental papilla, which are neural crest derived, differentiate into odontoblasts. These cells produce the underlying structure, the dentin, and the core tissue, the pulp. This process ensures the two hardest tissues of the tooth are formed in perfect juxtaposition and sequence.
As we transition away from the face and tongue, we have to cover the glandular systems that populate the throat and neck. Many of these, like the thyroid, are remarkable for their long developmental migration.
The thyroid gland has a distinct and unusual origin. It begins as a midline epithelial thickening, a diverticulum on the floor of the pharynx, near the junction of the first and second pharyngeal arches. This location is now known as the foramen cecum at the back of the tongue.
And then it begins its famous descent, a journey that takes it far down the neck.
It descends inferiorly, tracking caudally, passing anterior to the hyoid bone and the laryngeal cartilages until it reaches its final adult position anterior to the trachea. During this migration, it remains connected to its original site on the tongue by a thin epithelial tube called the thyroglossal duct.
And what's the fate of that duct?
The duct must completely atrophy and disappear. The developmental legacy of this migration is that failure of the thyroglossal duct to regress completely can leave cysts or remnants anywhere along its original migratory path.
From the tongue all the way down.
From the back of the tongue down to the thyroid's final position. These are known as thyroglossal duct cysts, and they're the most common developmental abnormality of the thyroid.
Furthermore, this gland becomes functional very quickly, doesn't it?
Remarkable so. The gland tissue itself starts synthesizing colloid and thyroid hormones around weeks 11 to 12. This means that if a fetus has a thyroid developmental defect, they can begin to suffer from hypothyroidism very early in gestation, highlighting the immediate importance of this descending endocrine organ.
Let's revisit the parathyroid and thymus migration, originating from pouches 3 and 4, and reinforce that position reversal.
The positioning of the parathyroid glands is one of the more confusing points for students of anatomy. But developmentally, it makes perfect sense. Pouch 3 gives rise to the inferior parathyroid glands and the thymus. Since the thymus must migrate aggressively all the way down into the thorax to perform its immune function, it pulls the pouch 3 parathyroids further down the neck, establishing them in the inferior position.
And pouch 4, which starts caudally to pouch 3, ends up superiorly.
Exactly. Pouch 4 gives rise to the superior parathyroid glands. Because pouch 4 doesn't migrate as far as the pouch 3 thymus complex, these superior parathyroid glands ultimately end up in a slightly more cranial position. This reversal is purely a factor of differential migratory distance.
A quick summary of the lymphoid tissue and salivary glands that establish themselves in the oral cavity.
Lymphoid tissue aggregates around the endodermal pouches. The palatine tonsil develops prominently from the mesenchymal investment of the second pharyngeal pouch. This is our primary tonsil.
And the adenoids.
Additionally, the pharyngeal tonsil, or adenoids, develops from the roof of the pharynx, and the lingual tonsil develops from the floor of the tongue, completing what's called Waldeyer's ring of immune tissue.
And the essential salivary glands, which start around week 6.
The three major pairs of salivary glands, parotid, submandibular, and sublingual, develop from bilateral thickenings of the oral ectoderm and endoderm. These thickenings invaginate into the underlying mesenchyme, forming the secretory components and creating ducts that open into the mouth. The parotid gland is the first to form, around week 6, followed sequentially by the submandibular and then the sublingual glands.
Now that we've built the soft tissues, the nerves, the blood supply, and the face, we need the protective structure, the skull. This isn't a single uniform bone. It's two functionally distinct parts, developed through two completely different ossification processes.
The complexity of the skull reflects its dual role, protecting the brain and supporting the face. Functionally, the skull is divided into the neurocranium and the viscerocranium.
Define those two parts for us.
Okay, the neurocranium forms the protective case around the brain. This includes the vault, or calvaria, which is the roof, and the base of the skull, the floor. The viscerocranium forms the facial skeleton, including the jaw, nose, and ear ossicles, and is derived primarily from the secondary mesenchyme of the first and second pharyngeal arches.
Let's start with the base, the chondrocranium. This is the temporary cartilage scaffolding that supports the brain before it hardens into bone.
The skull base is formed via endochondral ossification. This means cartilage is laid down first as a temporary scaffolding, which is then gradually replaced by bone. This process is slower and more structurally rigid than the direct bone formation we see in the vault.
And it comes from multiple sources.
It develops from three major segments, which directly reflect their cellular origins. First, you have the segments derived from the neural crest master builders.
What's that called?
That's the precordial chondrocranium. It is formed exclusively by neural crest cells and relates to the nasal capsules, the ethmoid bone, and the parts of the sphenoid bone anterior to the pituitary gland. It essentially forms the forward part of the skull base.
And next, the parts derived from the standard paraxial mesoderm.
That is the chordal chondrocranium, formed by mesoderm originating around the notochord. It formed the bones related to the pituitary fossa, the body of the sphenoid, and the petrous part of the temporal bone. And finally, posterior to that, components derived from the occipital somites contribute to the base of the skull, specifically components of the occipital bone.
So the skull base is a patchwork, with the anterior region built by NCCs and the posterior region built by mesoderm. Why the dual origin?
The NCC-derived bones, the precordial ones, have a distinct molecular signature, reflecting their developmental freedom. The mesoderm-derived bones, the chordal ones, interact more closely with the developing brainstem and spinal cord. This dual origin suggests different mechanical and signaling requirements for supporting the forebrain versus the hindbrain structures.
Now for the roof of the skull, the calvaria, which uses a completely different method, forming bone directly.
The calvaria, the protective skull roof, is formed by intramembranous ossification. This process is rapid and completely bypasses the cartilage phase. Mesenchyme, which is mostly neural crest derived in the frontal region, is converted directly into flat sheets of bone.
Which bones are created this way, and what are the specific benefits of this method?
These are the large flat bones covering the brain, the frontal bone, the parietal bones, and large parts of the temporal and occipital bones. Intramembranous ossification allows for rapid expansive growth, which is absolutely essential because the brain grows faster than any other structure in the developing human head.
The most famous feature of the calvaria is the joints, the sutures, and fontanelles, which are crucial for both birth and subsequent growth. They aren't simply gaps. They are highly regulated, specialized fibrous joints.
They are critical developmental features. The sutures, which are the fibrous joints connecting the bones, and the larger membranous areas, the fontanelles or soft spots, serve two absolutely crucial functions that define early life.
Let's start with the function during birth.
First, they allow for molding. During passage through the narrow birth canal, the flexibility of the skull, the ability of the bones to overlap slightly at the sutures, allows the fetal head to deform, reducing its circumference and preventing catastrophic injury to both the fetus and the mother.
And the second function is postnatal.
The second, and perhaps more sustained function, is accommodating the staggering rate of brain growth postnatally. Human brain growth in the first 2 years is explosive. It doubles in mass. The sutures and fontanelles remain patent or open for significant periods, allowing the bony plates to move apart continuously to prevent restriction of brain development.
When do they close?
The anterior fontanelle typically closes around 18 to 24 months, and the posterior fontanelle much earlier, within the first few months.
And even the joints themselves reflect the heterogeneous origin of the skull, tracing back to the neural crest and mesoderm.
Yes, the fibrous tissue of the sutures reveals the underlying cell sources. For instance, the coronal suture, which separates the frontal bone, which is NCC-derived, and the parietal bones, is derived from neural crest mesenchyme.
And the sagittal suture.
In contrast, the sagittal suture, which separates the two parietal bones along the midline, is derived from paraxial mesoderm.
What does that difference in cellular origin imply?
It implies that these sutures are regulated by different signaling pathways, which must communicate precisely to ensure balanced growth. If one suture closes prematurely, a condition called craniosynostosis, the other sutures may compensate by excessive growth perpendicular to the closed one, leading to an abnormal head shape.
This entire journey highlights the incredible complexity, but where there is immense complexity, there is also potential for failure. Our final segment has to address the clinical implications, which tragically reinforce the segmented nature of development.
Understanding the meticulous architecture we've just discussed is essential for pediatric medicine. When a defect occurs, it usually traces back to the failure of a specific developmental module, an arch, a specific stream of neural crest cells, or a critical fusion line. The error is rarely random.
Let's start with defects related to the first few arches, which define the look of the face.
We refer to this category as the first arch syndrome, exemplified by conditions like Treacher-Collins syndrome and Pierre-Robin sequence. These involve developmental defects, often linked to insufficient migration or proliferation of the neural crest cells that form the first pharyngeal arch.
What are the resulting features?
These conditions involve hypoplasia, or underdevelopment, of the skeletal structures derived from the first arch, specifically the mandible, the zygomatic bones, and the small bones of the ear, the malleus and incus.
So it's a package deal.
It is. And because the second arch is closely related and its NC migration is often also affected, defects frequently extend to the stapes, the styloid process, and the facial nerve, causing functional deficits in facial expression or hearing. The fact that the defects appear as a packaged jaw, cheek, and ear bones is a direct reflection of their single embryonic origin.
And what about the persistence of those external clefts that were supposed to disappear in the neck?
As we discussed, clefts 2 through 4 should regress completely, covered over by the descending second arch. Failure to do so leads to pharyngeal cleft anomalies. The most common manifestation is the appearance of lateral cervical cysts or branchial sinuses.
And they show up on the side of the neck?
Often as firm, palpable swellings on the side of the neck, running parallel to the anterior border of the sternocleidomastoid muscle.
These cysts are literally persistent remnants of the embryonic gill structure.
They are. They are epithelial line tracts, corresponding directly to the incomplete regression of that ectodermal groove. Identifying their location helps surgeons trace them back to their origin near the tonsil or pharynx, providing a perfect anatomical correlation with a failure in developmental regression.
Moving to the skull structure, we discussed the necessity of the suture staying open for brain growth. What happens when they close too soon?
That condition is craniosynostosis, the premature fusion of one or more cranial sutures. Because the brain continues its rapid growth, it compensates by expanding aggressively perpendicular to the closed suture, resulting in a misshapen skull. For example, a long, narrow head if the sagittal suture closes prematurely.
And this often has a clear genetic component, hitting those signaling pathways we mentioned.
Yes. The sources point out that craniosynostosis is often linked to mutations in growth factor receptors, specifically FGFR mutations, which disrupt the critical signaling between the mesenchymal cells of the suture, accelerating the ossification process. It's a perfect illustration of how vital the timing of bone formation is.
Our journey began by highlighting the complexity of building the head. After tracing the NCCs, the arches, the pouches, and the arteries, what is the grand developmental theme we should take away from this?
I think what stands out here is the extreme level of cellular and structural cooperation. The head is arguably the most striking example of a chimera in the body. It is a mosaic built from at least 4 separate cellular lineages: the mobile neural crest, the segmented paraxial mesoderm, the specialized ectodermal placodes, and the endoderm lining the gut tube.
So it's not a single sheet of clay being molded, it's 4 different sculptors working simultaneously on the same piece, each providing a specialized material.
Exactly. And these sources must engage in continuous, precise communication, migrating streams, crossing paths, differentiating into bone, cartilage, nerve, and gland, fusing perfectly in the midline and selectively regressing where necessary.
It's just an incredible level of control.
The sheer number of interacting parts, from the nerve that supplies the jaw to the cell that makes the ear bone, is a testament to the integrated nature of human development.
The development of the head and neck is truly a microcosm of human embryology, a dramatic story of segmentation, migration, fusion, and selective loss, all compressed into the critical first trimester. It gives us a profound appreciation for the precise orchestration required just to form a functional jaw, ear, and face. That was an immensely detailed journey. We followed the path from a few streams of migrating neural crest cells, guided by the hindbrain's rhombomeres, through the formation and remodeling of the 6 pharyngeal arches, the complete replumbing of the great arteries and veins, and the delicate fusion required to build the face and skull.
We did.
We've solved the complex wiring puzzle of the tongue and the functional connection between chewing and hearing.
So this raises an important question for you to consider. Given the incredible number of structures derived from the pharyngeal arches, from the tiny stapes in your ear to the complex cartilage in your throat, what would the human skull and neck look like today if Arch 5, which is currently rudimentary and vestigial, had never regressed and instead had contributed an additional fully functional segment?
Think about the implications. That extra segment would entirely restructure the anatomy of the upper respiratory tract. Would we have an extra set of facial muscles, a 4th ear bone, an additional pair of glands?
Maybe.
Would our neck be longer to accommodate the extra vertebra that might accompany that arch?
It's a compelling thought experiment rooted entirely in the highly segmented nature of our development. It forces us to consider how close our current anatomy came to being radically different. The sheer power of developmental regulation is that it knows not only what to build, but also what to discard.
Until the next deep dive, keep connecting the dots.